Hello, so we're back on section 3.3. We're working through all this finding the zeros of polynomials. In the last however many segments we've been in now, you might be noticing quite a few. These were very time-consuming problems. So I took a little extra time in the videos to work through all of those steps and hopefully had multiple problems. So hopefully you got bored of that and you're like, I've got this. It's just, no fun, but I've got it. So I hope you feel that way. If not, reach out to me. But we're going to move on to some nicer rules, some easier, less time-consuming rules in section 3.3. So on your note packet, find the page that says cut and bounce rule. I just love this rule. I just think it's really neat that the graphs do this. Whenever you're graphing a polynomial, like on number 9, if all of the zeros are just there an odd amount of time, which these are just there one time, which is common. If all of your zeros or all your factors are just there once, like this is to the first degree assumed, then all of those zeros, those are considered linear zeros, no multiplicity or just multiplicity 1, they're just gonna cut through the graph. We can use the zero factor property and find the zeros at -1. This would be at +1/2, and this would be at 3. So there's 3 real zeros. If you type that in your graphing calculator, you should see the graph crosses at -1, at 1/2, and at 3. And it does something sort of like that. It would be an odd degree, a third degree polynomial with 3 real zeros cutting through the graph. So this is the cut rule. If you have an odd multiplicity equals cut through the graph. When it's an even multiplicity, like on the next example, it bounces off the graph instead of this. All right, so let's look at the next one, number 10. So the next rule demonstrates, and again, feel free to use your graphing calculator to see this as so on your own screen. But number 10, we have a polynomial with a bounce. This would be a third degree polynomial. X squared is like having x times x, so there's x there twice. X equals 0, but repeated. So we call that a multiplicity of 2. The multiplicity is the exponent part. Again, so this would be just the origin. It's going to go through the origin when you don't have a number by it. It's like x plus 0. So the origin, or 0, is the x-intercept, but it bounces there. And then this is just there once, so that'll be x is 5, and that will cut. This one bounces, again, because of the even multiplicity, and this one bounces, or did I say this one bounces and that one cuts? That's what I should say. Again, check it out on your graphing calculator. We should look at this and know that there is an x-intercept at 0, but it's going to either bounce on top or under it. And I'll show you how to tell that in a second. 1, 2, 3, 4, 5. So it's going to cut either this way or this way. Now the way to tell is by the end behavior rules. So the end behavior rule says if you have an odd degree, so this is 2 plus 1, so this is third degree. In third degrees, the ends split. The ends always split, just like a line. A line is to the first degree. The ends split on a line, either a positive slope or a negative slope. So here we have an odd degree, third degree polynomial. The end should split. It has positive lead coefficient. Nothing about that should make it negative. There's no negative in front of that. So it should be a positive split, negative and positive. So the graph starts down. We should bounce a little bit. You don't really have to know exactly how far to bounce that down, but it will bounce and go down somewhat and then cut back through at this +5. All right, so you all try number 11 and 12. Try to do it, on your own analytical terms, figuring it out, sketching it, and then also check it on your graphing calculator. I'm going to go ahead and reveal the answers, though, going on. So on number 11, all of these are odd amounts. This is an x equals 0, repeated 3 times, or multiplicity 3. And then this is x is 5, just there once, and x is -2, just there once. So all of these are cutting through the axis. These are all cuts. So cutting through at 0, the origin, it's either going to cut this way or this way. And you have to figure out how to do that by looking at the end behavior, which we will in a minute. Then 1, 2, 3, 4, 5, and then at -2. So this is a 5th degree polynomial. If you count up all of the zeros you've accounted for, you've got 0 here, but you count it 3 times. So triple count it, plus that's there once, that's 4, and that's there once, that's 5. So you've got 5th degree if you add up all the zeros you've accounted for. That's a 5th degree polynomial, and again, it's positive in the front, so it should be down to up. That's the end behavior is down to up, just like the last one. So we start down, all of these should cut, something like that. It could have another turning point in there. Since it is 5th degree, it can have 4 turning points. So I could have an additional, or even there, it could wiggle. You know, I call them wiggling, but they're really turning points in the graph. Up to 4 turning points when you have 5th degree. You have n-1 turning points. Possible. It doesn't have to, but it could. So, but anyway, you'd have to look at the graph to determine that, or sketch some points. All right, number 12. Number 12 takes us back to the shifting rules, the old shifting rules. They're still a thing. If a problem qualifies in a shifting rule pattern, we can use shifting rules. So this is y equals, and this is what I consider a shifting rule. You've got something in the parentheses, that is a horizontal shift. It's always the opposite, and that would be a vertical shift. I want you to notice this is not in factored form either, so we can't say x is -1 is one of our zeros. We've kind of been leading through all the problems. They've been in this factored form, and we just set each problem equal to 0, but you could not do that here. So I wanted to highlight that. Anytime there's a loose plus or minus, it breaks up the factoring. That does not count as being in factored form. Again, you have to have only parentheses and times. Like that's times, that's okay, but having a +1 on the end is no longer in factored form. So you cannot use the zero factor property on that actually. But we have the shifting rules, and this is in the pattern for the shifting rules. So this graph, it sort of looks like a parabola. It's not officially a parabola. X to the 4th, it's just very similar looking graph with a little different curvature to it, but very similar looking parabola look. It's moved back 1 place and up 1 place. So shifting rules. Then this would flip it upside down and make it a real skinny graph. So we could think of this as being like a parabola. Back 1, up 1. That's where its shifted turning point is. And then the graph is upside down and pretty slim. So something like that. Again, check it out on your graphing calculator. All right, moving on down. The next section is going to ask us to list the zeros and their multiplicities. And some of these are already in factored form, which is very helpful to us. So let's look at those. Number 13, based on what we've been doing, again, try to think of what you think the answer is before I reveal the answer to kind of be active with me. Even though we're across the screen, pretend you're sitting in class and we're interacting, and see if you can answer these questions ahead of the reveal. Well, anyway, this does count as being in factored form. We've got a parenthesis times a parenthesis, no loose plus or minus signs. We can use the zero factor property and set each one of these equal to 0. So this becomes x is 3, that's its x-intercept, and x is -2. Basically, we change its sign when they're linear factors. X to the first, we can just throw that across the equal sign, so it changes its sign. Then this exponent is its multiplicity. So remember, the multiplicity is the outside exponent it's raised to. That means this parenthesis 4 times. So we'd say x equals 3, multiplicity of 4. That's going to bounce, right? The even multiplicities bounce off the axis if they ask that. Over here, this is a multiplicity of 3. It's repeated 3 times. So this will cut through the axis. But if asked what degree that makes it, altogether, that's 7th degree. 4 degrees accounted for here, plus the 3. Altogether, if we did have to multiply that out, it'd be 7th degree. Like in our other videos earlier in the section, we did a lot of multiplying. So 7th degree would really be a pain, if you can imagine. Okay, try number 14. Same question. F of x equals x plus 1 squared, x minus 3 cubed, and x plus 7. So here we have x is negative 1, multiplicity 2. So it bounces there. X is 3, multiplicity 3, and x is negative 7, multiplicity just 1. So these are cuts, and this is a bounce if we were graphing. Okay, number 15, f of x equals x squared minus 9, x plus 2 to the third. So set each part equal to 0, x squared minus 9 equal to 0, multiplicity is only 1 there, and then x plus 2 equal to 0. That's a linear factor, so we can just change the sign. It's negative 2, multiplicity 3. Over here, we ran into a quadratic. So how do you solve a quadratic? A couple of ways. We have methods. You've got the big old formula you can do, but no reason for that. Here, we can just throw the 9 across the line, square root each side, and it's plus and minus 3. So there's no repeated answer there. Notice these are unique, positive 3, negative 3, and nothing is repeated, just multiplicity 1. So we've accounted for 1, 2, plus 3, 0, so that's 5th degree polynomial. There, if we were graphing. Okay, number 16, one more of these to practice. Number 16, we've got f of x equals another factored polynomial, partially factored. Partially factored. Right here, this is a quadratic equation that actually would factor for you, or you could use the quadratic formula, but these solutions will be repeated twice. So we've got 2 solutions for the quadratic. Each of those solutions is multiplicity 2, which makes 4 degrees accounted for right here, plus 3 degrees there, so it altogether would be 7th degree. So setting, and this negative 2 is the lead coefficient. It affects whether it starts up or down, it's flipped, or if it has a steeper slope, but it does not give you a 0. This gives you a 0 at the origin. If there's no number beside it, that means it's at the origin. It's x plus 0, which makes a 0, 0, 0. So, but it's multiplicity. Multiplicity 3. So this stuff, x squared minus x minus 6 set equal to 0, we have to solve that with one of our quadratic methods. So this one actually factors, but if you hate factoring, you can always use the formula. So we get 2 solutions to our quadratic, as we should. It's a quadratic, and each of those solutions has a multiplicity. Each of those solutions is repeated twice. So count it all up. We got 2, 4, and 3 7th degree polynomial, if you were asked to name the degree. And then the lead behavior, because it's negative, it goes up to down. It splits like a negative sloped line. All right, so that's how we talk about multiplicities and graphing, whether it cuts and bounce, and all of that kind of fun stuff in there. On the next video, we've got one more thing to do in section 3.3, and that's how do you find the rational zeros with synthetic division. So we're going to come back in, one more kind of thing to learn, so I'll see you in a minute.